In this lesson, I'll give you a little insight into your future calculus studies, which I highly recommend for all of you. And as long as you know about simple polynomials like this, like the quadratic polynomial here shown, and if you know about how to calculate areas and volumes like we've done in many lessons before, then you're ready for this lesson. So what we have here is a quadratic polynomial, and that's defined by this one term only I can see here, and that's just going to be, the equation is going to be y is equal to 0.2 x squared. Alright, so I plugged in the values of x and I found the value of y, and that's how I was able to plot these points along here to draw the curve. Alright, so there's no other terms here. The constant term is not set, the linear term is not set, only the squared term is set, which makes it a quadratic polynomial. Alright, so what it's saying though is find the area beneath the polynomial shown. It says find the approximate area between 0 and 1 on the x-axis. Alright, here's 0 and here's 1 on the x-axis, and between 0 on the y-axis, which would be here, and between the quadratic polynomial. So it's looking for this area from here on the polynomial down to here and then back over to 0 again. That little space all in here, we're trying to find the area for that. Well, that's not quite as straightforward as finding the area of a rectangle or a triangle or a square or even a circle for that matter, because now we have a curve to deal with up above here. So somehow that curve factors into this equation somehow. So what we want to do is find that area. So let's get a secant line for starters, and let's see, I'll just bring one in here. You recall the secant line from some of the other lessons, whereas in this case we'll run our secant line between 0 on the x-axis and 1 on the x-axis here. So it's like that, those 2 points, and that's the 2 points I'm dealing with for starters. And we won't need the secant line. I'm just showing you what we're actually using. Is that'll be our limit there, that'll be our lower limit, and that'll be our upper limit of the secant line, like that. Alright, and then but to find it, let's see if we can use an existing object. Let's try finding the area by, well, let's get like a rectangle. Alright, so we'll put a rectangle in there. Now this rectangle happens to be, you know, well, if we use the rectangle, I'm showing this here as what I say is the approximate integral is equal to 2, but what this is actually calculating is the area of this rectangle right there. And if you imagine that it being 0.2, that's because that is 1 unit on x and 0.2 units up, like that. And if to maybe make it clear, I'll just change the polynomial for a second and show you. I'll just raise the polynomial, so there's 0.4, maybe I can get it way up there. There it is. So if I was taking it between 0 and 1, if my lower limit was 0, my upper limit was 1 here, and then in this case, you know, my rectangle, you can obviously see it's a 1 by 1 square, so the area is equal to 1. I just call it the approximate integral for the moment. So let's bring it back down to our 0.2x squared equation, which is what we'd use them. So if that's the area of the rectangle, well, that kind of approximates this. It kind of approximates the area under the curve, except all this part of the rectangle doesn't really count. So it's way too much of the rectangle to try and do it. So, but this part of the rectangle would count. So let's divide it up. Let's divide it into 2 rectangles. All right. And when I do that, in fact, let's do something else. Let me zoom in a little bit here. Let me see if we can scale this up a little bit so it makes it easier to see. It's a little bit better. Alright, so now I have 2 rectangles. I've just divided it between those 2 points like that. And now, instead of, before this whole part was above the curve, and this part was not, but now it says the area that it's calculating is 0.125 instead of 0.2. So what I've done is I'm calculating the area of this rectangle, and I'm calculating the area of this rectangle, and I'm just adding them together. And then that gives me this area of 0.125 that I call the approximate integral, like this. Okay, so now, in fact, let me move that approximate integral sign over just a little bit. So it's a little, let me see, I can do that. I'll just move that here, 0.5 in the x-coordinate. I think that'll do it. So when we move it, I'll go up to 3 rectangles. Okay, now I have 3 rectangles here. So now I've divided that interval into 3 spaces. Here's my lower limit of 0 and my upper limit on x of 1, like that. And then, so now I'm calculating this rectangle, that area, and I'm calculating the area of this rectangle, and I'm calculating the area of that rectangle, and I'm adding them together. And now look at that. The area is 0.103. All right, it's getting smaller because it's getting closer to this curved area down here. And it still looks like a bunch of rectangles, but now let's add a few more. Let's add maybe 5 or 6. Here's a bunch. Now suddenly, look at how our areas come down to 0.0816. And suddenly these rectangles all together are still doing the same thing. I took this one, I took the length and the width of this one and got the area. I took the length and the width of this one, got that area, length and width of that one, and then I just added them all up together. But now it's kind of looking a little bit like this curve here on top, because just these little pieces are above the curve. So let's just keep cranking it up, and let's watch what our approximate integral is, our area is, and it's 0.8. So we'll keep cranking it up. Let's get some more. I'll just put a bunch in there. Now I'm up to 26 rectangles in there. Now, in fact, I'm even going to zoom in a little bit more for you. Let's see, we'll zoom it way up now like this. I'll have to move my approximate integral label down here a little bit. Hang on. I'll move that down to 0.2 so we can see it. Let's see. Whoops, maybe that was a little bit too low. All right, hang on. 0.4. We'll move it to there. All right, that should work. And then maybe I'll move it over a little bit too. Let me see. Put it over here, out of the way. All right, that's just for my label, out of the way. Okay, that's better. So now I can see it. But now we have, here I've got 26 rectangles. All I'm doing is I'm taking the individual area of each of these rectangles, and then I'm adding them all up, to all 26 of them. And now it's telling me the area of all of those together is equal to 0.07, because there's now a little itty bitty bit above the curve like that. Well, suddenly, just by using all these little rectangles, it's starting to approximate this area under the curve between 0 and 1 on the x-axis, and between 0 on the y-axis and the quadratic polynomial above it. All right, just by using a bunch of rectangles. So we're just going to take a bunch more. All right, we're going to crank it up. I'm up to 35. I'm up to 51. We're up to 67. Let me see, 79, 95. Watch how that area keeps shrinking. 115. Keeps going down and down, and we're getting closer and closer, because now you can see we're at 0.067. I don't even think these first 3 terms, maybe even 4th term's not even moving anymore. Let's see what's moving. Now we're down to the 4th term moving, so we're really getting tight. In fact, already you can see now that just by using lots and lots of itty bitty rectangles next to each other, I'm closely approximating the area underneath this curve, and that's exactly what I'm doing. I'm taking the approximate integral. That means the sum. Integral means the sum, and really what we're doing, we're summing up all those little rectangular areas together, and can only approximate it by using rectangles like that. When you get into calculus, there's actually a way to calculate it exactly, but we're not doing it exactly, we're doing it approximately. But you can see, because of the power of computers, when you use many computers, in fact I'll show you, I'm up to 218 rectangles right now. I'm at 238, 254, 274, 338. It's very fast. 362, 382, 406, 454, and 474 rectangles right there. You can't even see them because they're so small, and the area is getting very close to this. So if you actually were to calculate the actual area using what we call as the integral in your future calculus lessons, it would be very close to that number. We're just doing it numerically, and in many cases numerically is a lot more fun, and it gets you very close to your answer. I mean, how close do you need to be in this particular case? Okay, well that's it for this lesson. That just gives you a little bit of insight into what you're going to be doing with calculus, because this is pretty much one aspect of calculus that you'll be working with, is finding areas beneath a curve. All right, and I'll see you in the next lesson.